In the summer of 1956, a group of scientists submitted a proposal to the Rockefeller Foundation, asking for funding to hold a 2-month research workshop. The proposal contained a sentence that, in hindsight, is almost breathtaking in its confidence. They wrote that they believed a significant advance in solving the problems of artificial intelligence could be made by a carefully chosen group of scientists if they worked on it together for a summer. One summer. To solve intelligence.
They didn't solve it, but they did something that turned out to matter just as much. They gave the field a name, a founding document, and a set of ambitions that drove AI research, and eventually nearly destroyed it, for the next 30 years. By the end of this video, you'll understand what happened at Dartmouth in 1956, why it mattered, and why that summer's overconfidence is still shaping how we talk about artificial intelligence today.
Plain Machine, AI in plain English. We're tracing the complete history, from the very first idea all the way to the present. Let's continue.
Think about what it takes to found a new academic discipline. You need a problem that enough serious people believe is solvable. You need a shared vocabulary, a name for the thing you're all working on. And you need a founding moment, a gathering, a paper, a conference, where the field crystallizes from a loose collection of individual efforts into something recognizable as a unified pursuit. In 1956, artificial intelligence got all three at once.
The Dartmouth Summer Research Project on Artificial Intelligence was the brainchild of a young mathematician at Dartmouth College named John McCarthy. McCarthy had been thinking about machine intelligence since his graduate years and had become convinced that the problem was approachable, not in the abstract, philosophical way that had occupied thinkers since Descartes, but computationally, with programs, with actual machines. He gathered 3 colleagues to co-author the proposal: Marvin Minsky, a brilliant and contrarian mathematician at Harvard who would go on to define the field for decades; Claude Shannon, the inventor of information theory and one of the most formidable scientific minds of the 20th century; and Nathaniel Rochester, the principal designer of IBM's first commercial computer. These were not fringe thinkers. They were 4 of the most credible scientists in computing. When they said a problem could be solved, people listened. The name itself was McCarthy's invention. He chose artificial intelligence deliberately, partly to distinguish the project from what was then called cybernetics, Norbert Wiener's competing framework, and partly because the term captured exactly what the project was attempting: to make machines that could exhibit behavior we would call intelligent in a human. The conference ran through the summer of 1956 at Dartmouth College in New Hampshire. About 10 researchers attended at various points. Not all at once, not all for the full duration. The atmosphere was informal, seminar-like. There were no formal proceedings, no published papers as a set. What came out of it were not solutions. It was a shared conviction that the solutions were close, that the problems were tractable, that a generation of researchers had found their life's work. That conviction would turn out to be both the field's greatest strength and, eventually, its most consequential mistake.
The most concrete thing to emerge from the Dartmouth period wasn't the conference itself, it was a program that arrived just as the conference began. Alan Newell and Herbert Simon, 2 researchers from Carnegie Mellon, had spent the previous year building what they called the Logic Theorist. It was the first program designed to do something that had always been considered an exclusively human cognitive task: prove mathematical theorems.
The logic theorist worked by searching through possible proof steps, selecting those most likely to lead toward a valid proof, and building the argument incrementally. It proved 38 of the 52 theorems in Principia Mathematica, Bertrand Russell and Alfred North Whitehead's monumental 1910 work on the foundations of mathematics. For one theorem, it found a proof that was actually more elegant than the one in the original text. When Newell and Simon sent Russell a copy of that proof, Russell wrote back that he was delighted. This was not a trivial result. Proving mathematical theorems was understood to require insight, creativity, and logical rigor, things that were supposed to be distinctively human. The logic theorist didn't have insight. It had search and heuristics, and those turned out to be enough. Newell and Simon followed it with the general problem solver, a more ambitious program designed to solve any well-defined problem by breaking it into sub-goals and working backwards from the desired solution. It worked on a surprising range of problems: logic puzzles, chess positions, symbolic integration. The name was deliberately ambitious. They believed they had found something close to a universal problem-solving architecture. They hadn't. But in 1956, the results looked extraordinary.
To understand why the optimism of 1956 felt justified rather than naive, you need to understand the frame these researchers were working in. They weren't making wild guesses. They had just seen a machine prove theorems that philosophers had considered the exclusive province of human reason. They had a theoretical foundation. The Turing test had established that behavioral equivalence was the right target. They had early results that genuinely worked, and they had a compelling analogy. The brain is a physical system that processes information. Computers are physical systems that process information. Given enough complexity and the right programs, why would the outputs be different?
This is not an unreasonable argument. In fact, it is still the argument that serious AI researchers make today, with far more evidence behind it. The mistake in 1956 was not the argument. It was the timeline. Marvin Minsky captured the mood of the era with a prediction he made in 1967. He said, "Within a generation, the problem of creating artificial intelligence will be substantially solved." A generation. 25 years. He was not alone. Simon predicted in 1965 that machines would, within 20 years, be capable of doing any work that a human could do. These were not careless statements. They were the considered judgments of brilliant people who had seen the early results and extrapolated from them. The extrapolation was wrong, but to understand why it was wrong, you have to understand what the early results were actually demonstrating and what they were quietly concealing. The logic theorist and the general problem solver worked by searching. Given a problem, they explored possible moves or proof steps systematically, pruning paths that looked unpromising and pursuing those that seemed to lead toward a solution. This works beautifully on a certain class of problems that are well-defined, where all possible moves are known in advance, and where the solution space is small enough to search through in a reasonable amount of time. Proving theorems from Principia Mathematica fits that description. So does chess, within limits. What nobody fully appreciated in 1956 was how quickly the search space explodes as problems become more complex. The number of possible chess positions is larger than the number of atoms in the observable universe. The number of possible English sentences is infinite. the number of ways a medical diagnosis can unfold is enormous and deeply context-dependent. The problems the early programs solved were not representative samples of the problems the researchers hoped to tackle next. They were the easy ones, the ones where search and heuristics happened to be sufficient. The researchers took these results as evidence that the approach would scale. It didn't scale, not the way they expected. This gap between what the approach demonstrated and what it implied is the intellectual foundation of everything that happens next in this series. The first AI winter wasn't a funding problem. It was a physics problem. The universe of hard problems is vastly larger than the universe of problems search can solve. Now, here's what this actually means if you work with AI tools. The pattern that defined 1956 is the same pattern that defines every AI hype cycle since. Early results on tractable problems are extrapolated into confident predictions about intractable ones. The gap between the demo and the general case is underestimated. And when the general case proves harder than expected, the entire field takes the credibility hit, regardless of what the demos actually demonstrated. You are living through this pattern right now. When you hear a claim that AI will transform your industry within 5 years, the Dartmouth frame gives you a useful diagnostic. Ask, what problem is this claim based on? Is that problem representative of the harder problems in the general case? Or is it a well-defined, bounded problem where the current approach happens to work well, and the timeline assumes the approach will scale to everything else?
Scenario 1. If you are evaluating AI vendor claims for procurement, partnership, or investment, the logic theorist lesson is directly applicable. A system that performs well on a curated benchmark is not the same as a system that performs well on your actual operational problems. The benchmark is the theorem proof. Your operations are the general case. Ask to see performance on problems that resemble your work, not on problems designed to show the system at its best. Scenario 2. If you are managing a team deploying AI tools, the overconfidence pattern suggests a specific risk. Teams that see early wins with AI on structured tasks often assume the tool will generalize to unstructured ones. It frequently doesn't, not at the same level of reliability. The structured task is the logic theorist's theorem. The unstructured task is the general problem. Build in a validation step before expanding scope. Scenario 3. The decision framework. When assessing any AI capability claim, ask 2 questions. First, what specific problem was this measured on? Second, how similar is that problem to the problem you actually need to solve? The gap between those 2 answers is where AI projects most reliably fail. The researchers at Dartmouth weren't foolish. They were doing what rational people do with new evidence. They updated toward optimism. The lesson isn't to be pessimistic about AI. It's to be precise about what the evidence actually shows. So, did they solve intelligence in one summer? No, but they did something that turned out to be more durable. They established the terms of the problem. They named the field. They built the first programs, and they set the level of ambition so high that when progress slowed, the disappointment was proportional. Dartmouth was not a failure. It was a beginning, and like most beginnings, it contained the seeds of the difficulties that would follow. The logic theorist proved theorems. That was real. The general problem solver solved problems. That was real. What wasn't real was the assumption that these results meant the hard problems were nearly in reach. They weren't. They still aren't in the same form. But the field that began at Dartmouth in 1956 eventually found out why, and finding out why led to the insights that actually did change everything. Here is the one-line version of everything this video was building toward. In 1956, scientists asked for one summer to solve intelligence. They named the field, built the first programs, and badly underestimated the problem. That underestimation shaped the next 30 years of AI history, and understanding it is the key to reading every AI claim you'll encounter today. In the next video, we stay in this era because what happened immediately after Dartmouth is a story that deserves its own episode. The researchers went home from New Hampshire in 1956 with the conviction that they were close. They secured funding, they built programs, they made promises to universities, governments, and granting agencies. For a decade, things seemed to be going well. The programs got better, the predictions got bolder, and then the progress slowed, quietly at first, then visibly in ways nobody had anticipated. Video number 5 is about that decade of optimism, what was built, what was claimed, and the specific moment when the gap between promise and reality became impossible to ignore. Subscribe if you want the full arc. Each video builds on the last, but they're designed to work as standalones. I've put together a one-page AI glossary, 30 essential terms in plain English, free, link in the description. This is Plain Machine. Thanks for watching.